So at the end of the last video, I promised I would show how to do the marginalization integral, in which we integrate out sigma from the joint posterior probability for mu and sigma, so that we can get a univariate probability distribution for mu alone. In other words, we want to evaluate this integral. And so the first step to doing the integral is to do a change of variables from the sigma to 1 over sigma. And for the limits of integration, when sigma is 0, t will be infinity, corresponds to t equal to infinity, and sigma equal to infinity corresponds to t equals 0. And so the integral becomes sigma to the n is 1 over t to the n, so this becomes t to the n. And 1 over sigma squared becomes t squared. And d sigma is 1 over t squared dt, and the minus, I'll put it out front. And now we're going to get rid of the minus sign by just interchanging the limits of integration. So we're going to go from 0 to infinity. And I have t to the n, and I have a t squared in the denominator, so this will be n minus 2. And now since this quantity over here doesn't depend on t, it's just a scalar, it just scales t squared, I'm going to define a new variable that's rescales t. So we're going to let tau be t times n mu minus mu hat squared plus e transpose e to the 1/2, so that t squared, or tau squared I mean, will be just the quantity here in the integrand. And that means that d tau dt. And now we can do the change of variables. So this time when t is 0, tau is 0, and when t is infinity, tau is also infinity. So that doesn't change the limits this time. And t to the n over 2 will be tau divided by this quantity raised to the power of n minus 2. The n minus 2 divided by 2. And then I have the exponential term. And then the t squared times this quantity is just tau squared. And the dt is simply d tau divided by this quantity. And this quantity is the same one I have over here, so I can simply add 1/2 to this quantity. Well, this numerator here, I can pull it out of the integral because it doesn't depend on tau. So I'll have, and this will become n minus 2 plus 1 over 2 times the integral. And the nice thing is that this integral, whatever it is going to be some number, and so we can just fold it into the proportionality constant, which we're neglecting anyways. And so that means that we don't even have to evaluate the integral. And of course this probability distribution is going to have its maximum when mu is equal to mu hat, because this is a sum of squares, is a positive term, and since there's a negative in this exponent, this is going to be maximized when this quantity is at a minimum, which will happen when this is as small as possible, which is 0 when mu is equal to mu hat. Right? This is a quadratic term, so it's always positive. So 0 is its minimum, and it happens at mu equals mu hat. So this distribution that we've gotten so far is known as the student t distribution. But let's approximate it using Laplace's approximation before going forward. So remember that to do Laplace's approximation, what we do is we take the logarithm of the probability distribution function and expand the logarithm in a Taylor series and truncate at the quadratic order. And the expansion is done about the location of the maximum of the posterior. We can define L of mu logarithm of the probability. So the constant is the proportionality constant, which was multiplicative over here, and now it becomes additive when I take the logarithm. Okay, so the first step to doing the Taylor series is to evaluate the derivatives of this function, and we need the first and the second derivative. Times the derivative of the inside by the chain rule. And now we can take the second derivative. The minus will become plus. And then by the chain rule, I get another factor like this one from the derivative of the inside. And then the product rule, I took the derivative of this term, now I have this term multiplied by the derivative of that term. And the derivative of this one is just 2n. So I have minus n times the previous factor n minus 1, and the 2 will cancel with this 2, and then I have this quantity, the minus 1. And now I'm going to evaluate these three expressions at mu equals mu hat, because mu hat is the location of the maximum, right? This first derivative vanishes at mu equals mu hat, which is the conditions for having a maximum. And then L double prime of mu hat. So this first term here will vanish because it's multiplying a mu minus mu hat. So this vanished, I'm just left with this one. This quantity on the inside vanishes, so all I'm left with is minus n times n minus 1 times this expression, which is E transpose E. This is what I need to construct the Taylor series. First I'm going to define this quantity. Remember that E transpose E is the sum of the squared residual, the model minus the data, and for the model it's the particular model where mu is evaluated at mu hat. So this, just to remind you. Alright, so now the Taylor series plus L primed of mu hat is going to vanish because L prime is 0. So then I go straight to the second derivative plus higher order terms. And these I'm going to neglect. So this becomes approximately. This term here, which is some constant, this doesn't depend on mu. And so I'll just write the constant plus, and now here I'm going to evaluate. So L double prime of mu hat is minus n over s squared. The 2 comes from the half in the Taylor series. Now I have it L double primed and mu minus mu hat squared. And now if I want to get the probability distribution, I just re-exponentiate this quantity. Be a normalization constant. And the normalization constant will be 1 over the square root of 2 pi times the standard deviation, which is just s divided by root n. And so this is the posterior probability distribution. Approximate, I guess I should have written. So we can write an error bar and the best estimate. So mu is equal to mu hat plus or minus s over root m. And these are going to be our error bars. And that's an estimate of the variance. And mu hat, of course, is just the plain average, right? Mu hat is equal to 1 over n, 1 transpose d. This is the sum of the squared residuals. Okay, so one thing that I want to point out is that if we had known the precision of the measurements, so if sigma had not been an unknown, out here where we marginalized it, So at this point where we have the joint posterior probability, if sigma had been a known quantity, right, then we would not have needed to marginalize out, and this would have been the posterior probability. Because it happens sometimes that you do know the precision of your measurements. And in that case, the probability distribution of mu would have been simply because now we wouldn't have had to marginalize out the posterior probability distribution. And so now the error bar would have been mu would be equal to mu hat. The estimate would be the same average, but now the error bar would be plus or minus sigma over root n. So this looks a lot like this expression, except here we use the actual precision of the measurements. So S is an estimate of what sigma is. Okay, so we've seen the case where we know sigma and the case where we assume we know absolutely nothing about sigma. And now we're going to do a case where we know, or at least we admit what we really do know, is that at the very minimum we know that sigma is a positive quantity, right? It's a standard deviation and it can't be negative. So one way to deal with that is, instead of assuming a flat prior for sigma, we're going to assume that we have a flat prior for the logarithm of sigma. Right, because the log now goes from minus infinity to infinity. When as sigma approaches 0, this goes to minus infinity, and as sigma goes to infinity, this goes to infinity. So assuming a flat prior in the log of sigma is known as a Jeffreys prior. And so we're going to do, we're going to rewrite this in terms of sigma, and this d sigma should be equal to this is the Jacobian for the transformation of variables from sigma to log sigma. And so this is equal to, now this is a constant, so this becomes proportional to this quantity, which is just 1 over sigma. And so this will be our prior. So if we did that, then the posterior probability over here would have been and now we'd have an extra factor of 1 over sigma out here. So this would be 1 over sigma to the n minus 1, and everything else would be the same. And now when we do the marginalization integral, we would get over here so where we used to have a sigma to the n minus 1, we now have just a, sorry, where we used to have a sigma to the n, we now have a sigma to the n minus 1, and that gets rid of the minus 1/2 we had before. And so now our estimate for S squared instead of n minus 1. All right, so we have 3 cases. The error bar. Let's summarize. So this case is more accurate than this one, but you see that if n is large, it doesn't really make any difference. We have n minus 1 or n. And incidentally, this n minus 1 is the origin of your calculator having the n minus 1 choice when you compute the sample standard deviation. But I think it's better to use n always, because I think we do know that the standard deviation has to be positive, and therefore Jeffreys prior seems like we're a little bit more honest about what we know about the value, and so we get a little bit smaller error bar which is more accurate. But none of this makes much difference when n is sufficiently large. So only for very small sample size does this matter. Okay, we should maybe do an example in MATLAB, and I'll do that in the next video.